Hi, this is Kanchana Murthy working as Assistant Professor in SNS College of Technology. In this video, we are going to see about LRU approximation page replacement. In my previous video, we have looked why we need page replacement. That is why we need particularly LRU page replacement, and the terminologies used in page replacement like a page false, page hit, and dirty bit, and why we need the demonstration of page replacement, and the superstar algorithm LRU page replacement algorithm. That is, we are using a page uh, knowledge about the past one rather than the future, because the future is optimal page, right? And we have implemented in two ways. One is counter and stack, and we have demonstrated the stack, how LRU takes place in operating system. So in this video, we will move depth into the LRU approximation algorithm. So this is the harsh reality of system engineering, because pure least recently used requires special and expensive hardware support, and tracking of every single memory access slow down the system. Because of this, real world operating systems use LRU approximation algorithms. So the most basic approximation uses a simple reference bit. Means every page gets a single bit initialized to 0. Whenever the CPU references that page, the hardware automatically flips the bit into 1. So when we need to replace a page, the OS, that is the operating system, searches for any pages whose bit is still 0. So this evolved into the popular second chance algorithm, also known as clock replacement algorithm. So it acts as a standard first in first out queue, but treat it like a circular clock face. So a clock hands the point next to the next page to be replaced. So if that the page is the page a reference bit is 0, it get replaced immediately. But if its bit is 1, it gets a second chance. The operating system clears its bit back to the 0, leaves it in the memory, and moves the clock hand forward to the next page. So this is the brilliant way to approximate the least recently used with almost 0 overhead. So let's visualize this. So it shows the greatest diagram of check-in chance clock replacement algorithm in action. So think of moving arrow as a clock hand, inspecting frames in the circle. So it steps through pages one by one. If it sees the pages that has not been used recently, that is the reference bit is 0, it replaces it. If it sees the page that has been active, that is the reference bit is 1, it clears that bit to the 0 and passes over it. So giving it another cycle to life. So if all pages have their bit set to 1, the clock hand will simply loop around, clears everyone's bit, and end up replacing every first bit it started with. So it essentially falling back to the classic first in first out behavior. So there is another class of page replacement scheme known as counting algorithms. So these algorithms maintain a counter that tracks exact number of times the page has referenced. While they are not very common in modern operating systems, they are important to know for theoretical. So there are two flavors here. One is least recently used. So replace the pages with smallest reference count. It assumes that if page has not been clicked on much, it is not important. Second one is most frequently used, MFU. So works on the exact opposite logic. So it replaces the page with the highest count. The argument here is that a page with a small count was probably just bought into the memory a millisecond ago. So we should give it a chance to execute before throwing it away. So to push performance even further, the operating system uses page buffering algorithm alongside with the main memory replacement choice, page replacement choice. So the core idea here is to always keep a pool of free frame available in the background. Normally, when a page fault happens, the CPU has to wait for a victim page to be written to the disk before it can read the new page in. So that is double disk penalty. So with the page buffering, so when a fault occurs, the operating system reads the desired page into the already empty frame from the free pool immediately. So the process restarts instantly, only later when the backing store or disk is ideal. So does the OS select the victim, write it out to the disk and recycle that frame back to the free. Furthermore, it can remember what used to be in those free frames if the CPU suddenly requests the page that was recently evicted but has not been overwritten yet. So it can be pulled back out of the pool instantly without touching the hard drive, right? So imagine this is an assessment. So imagine a system with three frames and the page reference of 4324132. So right before the page one arrives, the frames are completely full holding 432. So looking back at the recent usage order from most recent to least recent. So 2 was used last, then 3, then 4 is our least recently used page. So when a page 1 comes in, which page should LRU replace, algorithm replace? So think about it. So the correct answer is C, right? So it replaces, 4. So LRU replaces least recently used and the page is 4. So let's summarize everything we learned in LRU and LRU approximation algorithm. So we cover core concept of page faults, dirty bits, page hits, and we explored page algorithms like LRU and LRU approximation and the performance evaluation metrics and the page buffering. Um, so if you want to study these topics further, kindly use these references. So, so thank you so much for watching. Keep learning. So thank you. Thank you so much.